In this video, we will talk about how to find absolute maxes and mins algebraically and using calculus. So I want to begin by defining a critical number. So a critical number, or sometimes this is called a critical point of f, is a number c that's in the domain of f, such that, this part's important, it's in the domain of f, that's really, really important, such that either, and now we could either have f prime of c be equal to 0, or f prime of c is undefined. Okay, so we have this definition. So I want to begin with sort of a warm-up problem to get comfortable with what critical numbers look like graphically. So I have this graph of a function, some function y equals f of x drawn here. And there are three different sort of values that I'm asking you about. One is when x is -2, one is when x is 1, and one is when x is 4. So the question is, which of the following are actually critical numbers of f? And circle all that apply. So it might be some of these, it might be all of them, it might be none of them. But think about this, try this. This is your warm-up problem for this video. Take about a minute and see if you can answer this. 4, 3, 2, 1. Pause the video. Pause it and try this for a minute. Alright, so hopefully you've done that. Hopefully you've paused it and really tried this for a minute. So part A, -2, that is a critical number. So I'm going to highlight this. This one works. And the reason for this, the reason why this one works is, if I were to take the derivative and plug -2 in, that means what's the slope of the tangent line when x is -2? But the slope of the tangent line when x is -2 is 0. I can see that based on my graph. If I were to draw the tangent line here, it's perfectly horizontal. So it's going to have a slope of 0. Okay, so this corresponds to a horizontal tangent line. And the other part about this that's important is -2 needs to be in the domain of the function. And I can see that it is in the domain of the function because there's a point there. Okay, so what about part B, 1? So this one is not. That is not a critical number. The reason why is this is not in the domain of f. Not in the domain of f. It might be really tempting to say, wait, my function is not continuous at 1. That definitely means that my derivative is undefined there. There's not even a point there, so my derivative would definitely be undefined there. So it'd be really tempting to say, wait, the second condition holds. F prime of c is undefined. But that's ignoring the fact that the definition says that c needs to be in the domain in the first place for it to even be possible to be a critical number, to even possibly be a critical point. If there's no point there, it can't be a critical point. Okay. And then finally c. So c is when x equals 4. And that is a critical number, or a critical point. And the reason is, when x equals 4, well, first off, it is in the domain. There is a point there. But when we take the derivative, this is undefined because we have a sharp corner here. There's no consistent way to draw the tangent line at a sharp corner. So that makes our derivative undefined. Alrighty. So now let's do an example where we actually find the absolute max and absolute min of a function. It turns out, to find them, we need this framework of a critical number, and that's why I began by defining it. All right, so we have this function. On the interval from -4 to 1, we want to find the absolute max and min. Okay, so here is the method. The method involves the key idea that when we have a function that's continuous on a closed interval like this, the only place the absolute max or the absolute min could possibly occur is either at a critical number of the function that happens to be within this interval, or at one of the endpoints. Okay, so it's a matter of breaking down our steps to find those possible points and then sort of testing them. Okay, so my first step is going to be to find the critical numbers of our function in the given interval. So to do that, I need to take the derivative. So our derivative here is going to be, it's a bunch of power rule. I'll get x cubed minus 3x squared. Bringing the 2 down, I'll get minus 9x, and then plus 27. All right, so we have the derivative. Now, let's find when f prime of x equals 0, or f prime of x is undefined. Okay, so we're in the process of finding these critical numbers. So to do that, I gotta set my derivative equal to 0, and then figure out when the derivative is undefined. The undefined part is usually easiest. In this particular case, this never happens. It never happens here, although in other problems it might. Typically what we look for is if there's a fraction, what makes the denominator 0? In this case, there's no fraction here, so we don't need to worry about the denominator being equal to 0. Okay, so let's set our derivative equal to 0 now. All right, so doing that, we get x cubed minus 3x squared minus 9x plus 27, and we're going to set that equal to 0. We're going to set that equal to 0. So this is now an algebra problem. There are 4 terms here. And a common technique to try to factor stuff with 4 terms is to try grouping. Grouping is a good strategy, sometimes, to deal with stuff with 4 terms, 4 or more terms. Now, if grouping doesn't work, we may have to try more sophisticated tools like something called the rational roots theorem and factoring with long division. But luckily for us, we don't need to worry about that here. Grouping will work for us here. Okay, so when we do this thing by grouping, often we may have to experiment with which order to group things. Like, do we want to group the first 2 terms together and then the last 2 terms together? Or do we want to do the first one with the third one and the second one with the fourth one? Or do I want to do 3 of them together and then keep one of them by itself? So we may have to play around with it a little bit. For this problem, it turns out grouping the first 2 and the last 2 will work. Remember our warning about grouping back from the first couple of weeks. Never put parentheses around the groups. If I were to write this like parentheses, I have changed the meaning. Putting parentheses like this means take x cubed minus 3x squared and multiply it by negative 9x plus 27. And that's not what I mean to say at all. I don't mean to say to multiply these. So instead of putting parentheses around them, I like to just put little underline brackets around the things I want to be my groups. And whoops, I erased the 7. Okay, so now for my first group, we can factor out x squared and be left with x minus 3. And from the second group, if we're a little bit keen, we notice that we can factor out a 9, but negative 9 is a little bit better because we'll be left with x minus 3. And that's the same thing. This x minus 3 is common in the second group and in the first group. And that's usually what we look for when we factor by grouping, to know that, oh, I have the right grouping. I have this common factor, so we can factor it out. Let's factor out the x minus 3, that common factor. And now we're at the leftovers. The leftover from the first group is, x squared. The leftover from the second group is minus 9, after I take out the x minus 3. Now let's continue to factor this. All right, so we have x minus 3 times x squared minus 9 equals 0. So x squared minus 9, that's a difference of squares. So we will get x minus 3 times x minus 3 times x plus 3 equals 0. So now I can see that x either equals 3 or negative 3. But remember, we're only taking the critical numbers that occur in the given interval, which was from negative 4 to 1. So positive 3 is not in the interval. This is not in the interval. So we ignore it. We ignore x equals 3 in our computation. So if we had a different interval that 3 was a part of, then I would still include it in step 2. But for our purposes, it's not in my interval, so I don't need to worry about it. All right, step 2. Step 2 is now just all algebra. It's just going to be, it's all arithmetic, really. So it's easier. Plugging the critical numbers that are in the given interval, and the endpoints of the interval, plug them into the original function f. When we do that, the largest output that we get is the absolute max. The largest output we'll get is absolute max, and the smallest output is the absolute min. Okay, so there's two types of points we're going to have to plug into the original function. We're going to have to plug in the endpoints of our interval. So the endpoints of our interval were -4 and 1. And then we're going to have to plug in any critical numbers in our interval. But we said that 3 was not in the interval. Only -3 is in the interval from -4 to 1. So we're only going to worry about the critical number -3. Okay, so step 2 says take these points now and plug them into the original function. Okay, so I'll start off by plugging in -4. So the original function, if I plug it in, I'll get 1/4 times x to the 4th, so -4 to the 4th, and then it's minus x cubed, so minus -4 cubed, minus 9/2 x squared, so I'll get a -4 squared here, and then plus 27x, so 27 times -4. And if we work out what this is, we end up with -52. All right, so we need to do the same thing when we plug in -3 and 1. Okay, so if we plug -3 into our original function, I'm just going to say what we end up getting. We'll get -297/4, which is, as a decimal, -74.25. If we plug 1 into our function, we'll end up getting 87/4. And as a decimal, that's 21.75. Okay, so step 2 says, all right, when we look at these, when you plug in your endpoints, and when you plug in the critical numbers that were within the interval into your original function f, the largest output that we're getting, which in this case is 21.75, that is our absolute max value. So the absolute max value is 87/4. It's the biggest possible output, and that occurs at x equals 1. The absolute min value, so -74.25, that's the smallest output we were getting here. Let me write that as in fractional form though. -297/4. If we wanted to write it in decimal form, it's okay. And this occurs at x equals -3. And that would be our answer. So one quick remark that I want to make about this type of problem is, and this is typical for a lot of stuff in calculus, but in calculus, the actual taking derivative portion isn't too bad. Like, especially once we have all our derivative rules, like this was just power rule, so it wasn't too bad. But even if we have to do things like product, quotient rule, chain rule, that stuff isn't too bad. It's pretty quick to take the derivative. The part that can be trickier is actually now setting this equal to 0, defined our critical numbers, and solving. And that's all algebra. And that's a big part of why we spent the first couple of weeks of this class reviewing our algebra. What typically can make calculus hard isn't the actual calculus, because taking a derivative isn't too bad. What can make calculus hard is the algebra. Like once you take the derivative, being able to set it equal to 0 and solve, that sort of thing. So when you have questions about problems like this, especially when it's the algebra portion, setting it equal to 0 and solving, definitely use our resources for help to ask about those. All right, in terms of our goals for this section, we have now talked about how to find the absolute max and min using calculus. So I call this algebraically. In the last video, we talked about how to find them graphically with the graph. In the next video, we will talk about how to find local maxes and mins using calculus. And that'll involve using what's called the first derivative test.